Hello, Professor Sargent here with you again. We're going to take a look at another example of applying the method of corners, this time to a minimization problem, specifically a standard minimization problem. All right, here we go. Now, to set something up for later, I want to remind you that in a previous video, we took a look at this maximization problem. It was a standard maximization problem. And what we found was that when we graphed the feasible region, there were 4 corner points. And when we checked the value of the objective function, the corner that gave the optimal solution was 120, 60 with a maximum solution for z of 2100. And I want you to compare that to this question. Now we're going to minimize c. This is actually a standard minimization problem, and we'll discuss a little bit later why it's standard. And I want you to notice that we've got some similar numbers here. That's going to be important in a later video. For example, we've got the 360 and the 300 that we have the constraints less than or equal to. Now they're showing up in that same order in the objective function that we're minimizing. We have the 1, 4 showing up as coefficients of A, and the 2 and the 1 showing up as coefficients of the B. And last, we're seeing the coefficients of the original objective function, 10 and 15, showing up as what the constraints are greater than or equal to. We still have non-negativity, which is going to trap us either in the first quadrant or on the axes, the portion of the axes bordering the first quadrant. Now, I've already graphed this, but I want to explain how I came up with it. I'm not going to rewrite the equations. Instead, I'm going to find intercepts, because those intercepts may be corner points. On the other hand, not all intercepts are corner points. So when I take the first constraint, I want to find the intercept of the boundary line, and so I set it equal to 10. And when we put in 0 for B, 2 times 0 is 0. A plus 0 is still A. So we have that A is 10. 10 comma 0 is the intercept along the horizontal axis. Putting in 0 for A, 0 plus 2B is 2B. So dividing both sides by 2, B is 5. We have along the vertical axis, we have 0, 5 as the other intercept. And we see that back here, 10, 0 and 0, 5. Then for the second constraint, again, setting it equal to 15 so that we can find the intercepts of the boundary line. And in this case, B is 0. We'll have that 4A plus 0 is 4A. So solve 4A equals 15. And 4 is something nice to divide by. I put it as a mixed number, but I guess you could put that as 3.75. No rounding is needed there. And that's going to be along the horizontal axis. Whereas if we put in 0 for A, 4 times 0 is 0. 0 plus B is B. So B equals 15. We get 0 comma 15 is the intercept along the vertical axis. So looking for 0 comma 15 and 3.75 comma 0, that's this boundary line. And the boundary lines are solid because we have the or equal to. Furthermore, there is a point of intersection here that we're going to have to solve for where that is. That could be a corner point. So since none of those lines is going through the origin, and by the way, it's not just from my hand-drawn sketch there that I know that, but also if I put in 0,0 for a test point and get exactly equal to what's on the other side, then I know that I am on that boundary line at my test point. So I put in 0 for A, 0 for B, do the arithmetic, and I get 0, which is not greater than or equal to 10. So for that first line, this one right here, I'm going to be shading the other side. This side has the origin. I'm going to be going this way instead. Same goes for the second constraint. Putting in 0 into the second constraint, I get 0, which is not greater than or equal to 15. So I do not shade for this line. I do not shade in this direction. I shade in that direction. And so our common intersection of shading is the portion that I'm already showing here. So our corner points are the 0, 15, the 10, 0, and this unknown intersection point right here. So I'm going to show solving for that intersection points. Remember, over here on the left side in the table, those are our equations of the boundary lines. I'm going to take those coefficients, 1, 2, and 10, and then 4, 1, and 15, put it in an augmented matrix. I've already got a 1 in the upper left-hand corner there. So I'm going to multiply by -4, everything in row 1, and add it to row 2. -4 plus 4 is going to give me 0. -4 times 2 is -8. -8 plus 1 is going to give me -7. And then -4 times 10 is -40. -40 plus 15 is going to give me -25. So here's the first result. Now I've got a unit column in the first column. Now I need a 1 along the diagonal. I need to turn that -7 into a 1. And so I'm going to multiply that and everything in row 2 by -1/7 to make that 1. It's not going to change the 0. And multiplying -1/7 times -25, I will get +25/7. So I already know the y coordinate, well, the b coordinate actually, of that intersection point. And now if I get the rest of that column to be a unit column, we're going to have to multiply that 1 down here in the bottom right by a -2 to add to the 2 and get 0. So overall, I'll do that to the whole row. Multiply row 2 by -2 and add it to row 1. -2 times 0 is 0. 0 plus 1 is 1. So I'll still have 1 there. Let's see, -2 times 1 plus 2 will give me the 0 I want. And then -2 times this will give me -57. I'll write the 10 as 70/7. So -50/7 plus 70/7 will give me 25/7. And that is going to give us the A coordinate of that point of intersection. So now we can see, although we were using the intercepts to help us with the graphing, not all of them are going to be listed when we look at corner points based on the intersection of the shading, the common shading, 0, 15, 27, 25/7, and 10, 0. Those are our corner points, just those 3. And when I plug that into C, let's double check what the formula for C was. So we're going to be multiplying 360 times the A coordinate and 300 times the B coordinate, and then adding. So 360 and 300. $360 times 10 plus 300 times 0, 3,600. Down here to the bottom one, 360 times 0 plus 300 times 15, 4,500. And then this, let me bring up a calculator. I could enter this two different ways. 300 times the 27ths. There we go. With parentheses around that. May or may not be necessary, but just in case, putting those parentheses. Actually, I think that was 350. And then 300 times the 25. And let me double check. over 7 and 25 over 7. Okay. Must have reversed those orders. Let me double check that. Just a moment. Oops, that was 360, not 350. So I scrolled up, pressed enter to copy and paste. I'm going to change that 350 to a 360. I should see that 2100 that I had in the table. Yes. Okay. Now, if doing this without much calculator use, then since 7 does not go into 360 or 300 nicely, what you could have done instead is this. Since both of those have a denominator of 7, we could take 360 times 20, much easier to do even without a calculator. 300 times 25, add those together, and then divide the whole thing by 7. Same result. Okay. Now, remember that we were supposed to minimize this objective function C. And putting those three values in order, 2100 less than 3600 less than 4500. So that minimum value of C is 2100 produced by 27ths, 25/7. Again, I'm going to come back to seeing some of the same coefficients as the standard maximization problem from the earlier video. But also, notice that that minimum value of C of 2100, that was the maximum value we came up with from that standard maximization problem. So not only are we seeing some of the same coefficients in this new minimization problem, just in showing up in different places, and we'll talk about what that pattern is, but also the fact that we came up with Z maximized at 2100 and C being minimized, the minimum value also being 2100. Hope that helps, and I'll see you in the next one. Stay safe and healthy.